In this video, we're going to discuss the concept of multi-step synthesis. So we've learned a series of individual reactions that are good for converting one functional group to another. Rarely, though, do we actually want to only do a single thing to a molecule. Often we have a starting material that we can obtain cheaply and readily, so something like this. But our goal is to make a reasonably different molecule. Now, if you have a single step that can go between these, excellent. But we don't know any tools that can go from a double bond to a ketone. So none of our reactions will do this for us. But there's no reason I can't chain two reactions together. Idea for this is I have a product I want to make. I don't have to make it from this starting material directly. I could make something in between. I could do one reaction to get some intermediate product and do another reaction to get our final product. Question then becomes, well, what could I do? What would that intermediate be? What would be in the middle? There's a lot of ways to go about this, but the most common method employed is what we call reverse synthesis. The basic idea is my double bond, my starting material, there are many things you could do to it, but really only one is going to get you this intermediate we need, and then whatever the intermediate needs might have many things that could be done, but only one is going to get us to our product. Instead of looking at all the possible reactions your starting material could do, let's figure out what reaction could give us our product. So I have a ketone, cyclopentanone. I want to make that ketone. What reactions give us a ketone? So instead of thinking the starting material plus a reactant makes a product, start with a product. Which reactions do we know can make a ketone? In this case, the only real tool we have for making a ketone is if you have a secondary alcohol. A secondary alcohol plus an oxidant will make a ketone. This is really the only way to make a ketone that we've learned. And so to make a ketone, I would have had to have started with an alcohol. I would have used some oxidant and I would have needed some alcohol. Well, what alcohol would give me cyclopentanone? Would have been a cyclopentanol. Cyclopentanol plus an oxidant would cause that oxygen and the carbons it's attached to form a double bond to the oxygen. And so one route that I could go would be to have cyclopentanol in the middle. Well, that still leaves me the question of what am I doing to get to cyclopentanol? Like, this is still not the thing we want to start with. We want to start with this cyclopentene. So now I have to look, is there a step that will go from cyclopentene to cyclopentanol? What I really have is a double bond. Can I turn a double bond into an alcohol? And there is a reaction for that. Generically, double bonds plus water will form alcohols. I have a double bond, I want an alcohol, I could add water. This is a reaction scheme. This is a synthesis route. There's a lot of names for it, but basically, you don't always go in one step. Sometimes we have to think about multiple steps, multiple different reactions, before we end at the product we want to be in, based on the starting material we began with. Multi-step synthesis comes up in many forms. The reality is there are usually many, many more steps than this. Standard drug synthesis can easily be 20 to 30 steps. Now, rather than draw them all out, we'll show a simpler one here, but you easily can have 20 to 30 steps in a drug synthesis. Each of those often is a couple reactions to protect a functional group so it doesn't react with a reagent that could affect multiple, and then deprotecting them. But nonetheless, it's a lot of individual components. There's a lot of loss. They are prone to hurting your yield, and as a result, we want fewer steps. The fewer steps you can make, the better your production will tend to be. This is a severe problem with specialty drugs like cancer drugs. Many of them can require 30 to 50 steps to make these specialized molecules. And so we put a fortune of material in and we get very little out. There's a reason some drugs cost a lot. And it's not always just pharmaceutical greed, though that is probably a fair bit of it. Let's take a look at this one. So this is actually the synthesis for a more common drug. If you want to make ibuprofen, we actually have to go through several steps. And so while there are many very complex reactions that can make ibuprofen, this is actually one of the modern chemical ones used in industry. And so there's a few reactions that we haven't learned here. But our starting material is this complete alkene. It's really just an alkane with a phenyl group on it, but it is nothing but hydrocarbons. In the right situations, if you've got, so acetyl would be this very reactive diester, so AC2O plus HF. Well, this does a reaction we haven't learned where you can actually attack one of the hydrogens on the ring, and it's able to attach one of those acetyl groups to the ring. And so you end up with this ketone coming off of your benzene ring. They can continue. They put in H2 and nickel. Now this is a reaction we have seen. This is reduction. We reduce something. Well, we go and look and say, hey, what got reduced? Well, the only thing that's different is that OH. It used to be a ketone. There's a reaction that says that if I have a ketone and I add a reducing agent, specifically H2 and either nickel or palladium or something like that, I can get an alcohol out of it. So this is what's happening here. We're seeing industrially employed our reduction reaction. A ketone is converting into an alcohol. And then the final step is another one that's an advanced industry technique. Carbon monoxide and palladium can actually attack and add itself in. And so you have a carbon here that was this carbon. It brings an extra oxygen and it attaches itself. It basically inserts between the O and the C that was already there. These are advanced organic techniques, but just to show a few ways that we can bring multiple techniques, some of which we can recognize and some of which are beyond the scope of this course, but that we stack them in order to go from one molecule to an intermediate molecule, and then we can just keep chaining intermediate molecules until we reach the molecule we want. So here's a nice 3-step reaction for an industrial drug. For our course, we will not be dealing with multi-step in any real detail. You'll be asked individual ones. You may at most have 2 steps on any exam. But the idea that you can link multiple reactions together in series, this is a fundamental component of not only organic synthesis in the lab, but biological processes. When you get to the Krebs cycle, citric acid cycle, or anything like that, there are many, many molecules and steps that go in as processes change, as you get to metabolism and you want to break down a fat. There are many, many individual steps that will allow the molecule to be changed, alter its functional group, make it more reactive, bring in a different reagent that wouldn't have done anything with the earlier steps. This is the idea of multi-step synthesis. It's really how you just continuously change molecules, shown here in a few smaller steps to get us going.